Hello everyone, my name is Zhen Wang from Polytechnico di Milano. The presentation is about investigation of the biaxial flexural fracture of aluminosilicate glass by smeared fixed crack method. The presentation can be divided into 5 parts. Aluminosilicate glass is one kind of inorganic glass widely used in the field of architecture, electronic devices, airplanes, and also defense structures. It may face different and complex loading conditions during service. Fracture failure is a typical fracture type for glass structures. The advantages of aluminosilicate glass include its low density and excellent transparency, high hardness, and also the compression strength. However, it has disadvantages such as its brittleness and low tensile strength, which can cause very sudden failure of glass structures. Numerical simulations together with experimental tests are essential for structure design, optimization, and evaluation. Different numerical methods have been developed to simulate the brittle fracture of brittle materials, but the finite element method remains the most mature and efficient one among all these methods. In this study, the bore-on-ring and ring-on-ring tests together with 3D DSA technique were utilized to obtain the biaxial flexure strength and full-field deformation of glass plate specimens. A finite element modeling approach incorporating smeared crack model is chosen to represent the discontinuous microcrack brittle behavior of aluminosilicate glass. This numerical method is carefully assessed and the capacity of this model is evaluated by comparing the results of the numerical simulations with the corresponding experimental tests. For bending tests, 3-point bending and 4-point bending tests are the simplest traditional flexural test methods. However, edge defects introduced during the specimen's manufacturing process may affect the testing results for bar-shaped specimens. Biaxial flexural tests have been developed to overcome this problem. Ring-on-ring and bore-on-ring tests are the most popular biaxial flexural test methods for brittle materials. The schematic drawing and stress calculation formulas of bore-on-ring and ring-on-ring tests are shown in this slide. It's well known that the displacement values provided by the loading machine during quasi-static compression tests is usually unreasonable, and it contains extra displacements due to deformation and free play of the machine. A special designed fixture with a 45-degree mirror was used for 3D DSA measurement in this study, which can provide full field deformation results of specimens. The test setup is shown in this figure. The third part is about the numerical method used in this study. For the numerical simulations in this work, smeared fixed crack finite element method was used. This method has already been implemented in the commercial software LS-DANA as material 280 glass. At present, only shell elements can be used in this simulation. Thus, the sufficient number of integration points over thickness should be used. Here is a schematic draw of one single element. If a certain number of integration points in one element failed, the whole element will fail. So the default value of integration points was used as 1, resembles the fact that a crack in a glass plate immediately runs through the thickness. the correct direction in the integration point, which field first sets the direction for the whole element, and also correct strain is computed individually in each integration point. The underlying material behavior before failure is isotropic, small strain linear elasticity with Young's modulus E and Poisson's ratio nu. Asymmetric failure happens as soon as one of the following plane strain stress failure criteria is violated. This is a schematic draw of the failure process of one single element. The crack is perpendicular to the first principal stress, and once a crack appeared in this element, the local crack coordinate system will be applied to this element. And the second crack can also occur, which is orthogonal to the first crack. And the cracks can open and close independently in this model. As I said just now, the integration points numbers are very important in this simulation. So we calibrate the number of integration points in this study. It can be seen from this figure that with the increase of the integration points, the flexural strength decreased and became stable. And also with the increase of integration points, the calculation time will also increase. To balance the simulation results and the calculation efficiency, 9 integration points were used for ball-on-ring and ring-on-ring simulations in this study. This is the effect of mesh size on the simulation results. It can be seen that the proposed numerical method is mesh independent. For ball-on-ring loading condition, the simulated flexural strength decreased slightly when the mesh size is smaller than 0.5 mm because of stress concentration induced by the point contact area between the indenter and the specimen. Also, with the decrease of mesh size, the calculation efficiency decreased remarkably. Finally, the mesh size 0.8 mm was chosen for the study. As the smeared crack model can only be used in explicit analysis in LS data, but what we want to simulate is a quasi-static loading condition. The numerical loading time must be sufficiently long to avoid the dynamic effects in this condition. So different loading speeds have been tried, and with the decrease of loading speed, less fluctuations can be observed from the curves. The loading speed 0.05 meter per second was used finally for all the simulations in this study. The fourth part is the results and discussion. This figure shows the deformation field of the ball-on-ring specimens from both tests and simulations. It can be seen from this figure that both the flexural stress displacement curve and the displacement distribution of the specimens at different stages can correspond well with the numerical results. Similar results can also be obtained by the ring-on-ring tests. Here provided the maximum principal strain distribution for these two loading conditions. Because the major maximum principal strain of the specimen is very small, so some fluctuations appeared in the experimental curves, but the trend is very well compared to the simulation results. Here is the maximum principal stress distribution obtained from the numerical models in this study. It can be seen that the bound-on-raying loading condition results in a gradient major strain and stress distribution on the glass surface, with a peak value in the center region of the specimen. In contrast, a uniform major strain and stress distribution field is formed below the load ring for the ring-on-ring specimens. These are the fracture and failure modes of specimens from experiments. For the bound-on-ring specimens, cracks initiated from the center of the specimen and propagated to the outer ring of the specimen. For ring-on-ring specimens, the crack region locates at the load ring of the specimen, and crossed cracks appeared at the inner ring area. Radial cracks formed along the outer ring area. This is the fracture modes obtained from numerical simulations. We have used 3 different kinds of mesh types for comparison. For structured quadrilateral mesh, straight cracks were formed in the specimen, but for unstructured quadrilateral mesh and triangular mesh, there are more cracks in the specimens, and also some discrete properties can be observed from the failure modes. This is the numerical results for the ring-on-ring specimens. It can be seen that both the crossed cracks at the inner ring area and the radial crack at the outer area can be very well reproduced, especially for the unstructured quadrilateral mesh and the triangular mesh, which is very comparable to the experimental observations. Finally, there are some conclusions for this study. In quasi-static bound-on-ring and ring-on-ring tests, a special designed fixture with a 45 mirror together with 2 cameras were used for 3D DSA measurement during the loading process. Reasonable in-plane strain distribution and auto-plane displacement field of the disc specimens can be provided by this novel testing method, overcoming the problem of inaccurate displacement data provided by the loading machine. During the loading process, a uniform strain distribution field is formed below the load ring of the ring-on-ring specimen, while a gradient strain distribution is built for the bound-on-ring specimens. The bound-on-ring flexural strength of aluminosilicate glass is higher than the ring-on-ring strength, while the ring-on-ring specimens can support greater deformation upon failure. Finally, radial cracks formed along the radius of the bound-on-ring specimen initiating from the center point. For the ring-on-ring specimens, cracks can be divided into 2 regions. Standard cracks formed in the inner ring, while radial cracks appeared in the outer ring area. The smeared fixed crack finite element method was utilized to represent the discontinuous macro crack brittle behavior of aluminosilicate glass. This numerical method is carefully assessed, and the comparability of this model is evaluated by comparing the results of the numerical simulations with the corresponding experimental results. Both the deformation field and the fracture morphologies of the plate specimens can be very well replicated. Thanks for your attention.